So yesterday we talked about energy, about work and energy, about different types of energy, forms of energy, that kind of thing. Okay, and then we briefly talked about thermodynamics. Okay, mostly just to define the word. Right, thermodynamics means energy changes. Thermo meaning energy, dynamic meaning changing. Right, so thermodynamics deal with any changes in energy. Specifically, thermodynamics deals with thermal energy. Okay, that stuff we have formerly called heat, and probably still do sometimes by mistake, myself included. Okay, so thermodynamics deal with heat, which is the transfer of thermal energy. So we talked about heat quite a bit, okay, and thermal energy as well. All right, so there's a fair amount of terminology in this lesson, so make sure if something is underlined or say, hey, this is an important term, that you highlight it or underline it or write it down depending on what you're doing there at your desk. Okay, so the laws of thermodynamics govern basically how things work in terms of energy and thermal energy specifically. Okay, the first law of thermodynamics is the law of conservation of energy. Energy cannot be created and it cannot be destroyed. Okay, it can be changed. Okay, it can be given. It can be lost. Okay, all of those kind of things, but it can never be created or destroyed. That's the first law of thermodynamics. Second law of thermodynamics talks about which way energy goes. And it always goes from the higher energy object to the lower energy object, from hot to cold. Okay, is most commonly what we experience with thermodynamics. All right, so to understand those things, we have to talk about a few terms. Okay, the first term is a system. Okay, we use the term system in physics all the time. Okay, a system is a set of interconnected parts. Okay, now a system is defined by kind of arbitrary boundaries. Okay, we could consider each individual in this room to be a system. Okay, that would make that person the system and everything else the surroundings. Or we could say that this room is the system and the walls are the boundary and everything outside of that are the surroundings. Okay? The boundaries are kind of defined by whoever is kind of doing the observing. Okay? So two people might look at the same situation and define a system differently. Right? So if I was looking at this room, okay, I would say it's the room that's the system, but another person might come in and say, no, each individual person is their own system and everything else is the surroundings. Okay, so the system is the set of interconnected parts, okay, and the boundaries, okay, can be changed, but everything outside of the boundary is considered to be the surroundings. Okay. Now, if you go outside and it's a super hot day, it's 40 degrees, how do you feel? Hot, yeah, that's the answer I was looking for. Okay, yeah, I wasn't trying to trick anyone. Hot, okay? Why do you feel hot? Because the surroundings are hotter than you are, temperature-wise. Okay, so you feel hot because thermal energy is moving from the surroundings to you. Okay, normally that's not the case. Okay? Normally, we're much hotter than the surroundings and energy flows from us to the surroundings. In the wintertime, okay, we try to prevent that, or slow it at least, by putting on extra layers or a big heavy coat or something like that, so that energy doesn't as easily move from ourselves to the surroundings. Okay? Later on in Unit 4, we'll actually talk about the methods by which that occurs, okay, and how we can kind of modify, prevent, and things like that. Okay, so we talked about systems, we talked about boundaries. Okay, there are three kinds of systems that we will talk about in physics. Okay, the most common type is an open system. Okay, an open system exchanges both matter and energy with its surroundings. Okay, that makes each of us an open system. Okay, because we inhale air and exhale air, and we change the composition of it in doing so. Okay, that's an exchange of matter with our surroundings. Okay, we also consume food and water and leave wastes behind. That's us again exchanging matter, okay, with our surroundings. And as we were just talking about, if I'm in like this room right now, the air temperature in here is about 18 degrees Celsius. That's colder than our body temperature. So we are right now exchanging energy with our surroundings in the form of thermal energy. Okay? You've probably noticed that every day when you come into this room, it's cold. I use you to heat it up via the second law of thermodynamics. Okay? Because I don't dare turn on the heat. Because the heat is either on or off. And there is no ventilation in this room. So if I turn on the heat, we'll all be in here in the other situation we talked about where the air is hotter than we are. Okay? Trust me, I know it's been that way ever since we moved in. But apparently it's getting fixed over Easter. I believe it when I see it. I'm a little pessimistic. Been fighting that battle 20 years. Maybe I get to win. Okay? So, laws of thermodynamics say that if you are an open system, you are exchanging both matter and energy with the surroundings. Okay? And there's no necessarily rule for which way it goes other than energy goes from hot to cold. Okay? Matter can go both ways. Now, a closed system is one that cannot exchange matter, so it's completely sealed, but still exchanges energy. So this would be basically any airtight container. All right, so if you made dinner and there was leftovers, okay, you would put them in like a Ziploc bag or a container that could seal, and you'd throw them in the freezer. All right, well, there's no exchange of matter between the inside of the freezer and the inside of the container because it's closed, it's sealed, okay? But does the energy in the leftovers still go to the inside of the freezer? Yeah, that's why eventually it freezes. Okay, we're actually going to talk today about how a freezer works, okay, in terms of the second law of thermodynamics. All right, so it can exchange energy, but cannot exchange matter. Okay, it's closed off, sealed up, closed system. The last type of system is pretty much theoretical. Okay? It's easy to make a closed system, but as far as we know or are capable of, it is impossible to create an isolated system, a truly isolated system. Because an isolated system doesn't just not exchange matter, it also doesn't exchange energy. That's the hard part. Okay? Sealing off matter exchange is easy. Just make it airtight and you're done. But completely insulating something against any exchange of energy is basically impossible, at least with our current technology. All right? So, to make something completely sealed against losing energy or exchanging energy with the surroundings would mean it can never, ever allow heat, okay, to be exchanged, okay, so a transfer of thermal energy, and it can never do any work. It can't ever exchange any mechanical energy either. Okay? That would mean it would have to be like perfectly frictionless, okay, so that nothing could ever do any work on it or exchange any energy, cause it to move. It would be completely isolated. The energy part is the part that we see as impossible. Okay. All right, now that said, we talk about isolated systems all the time in physics because it simplifies things. We don't have to worry about, oh, well, this is a perfectly isolated system. That means there's no friction, there's no thermal energy being lost. It just simplifies the situation and allows us to kind of work on concepts versus reality. And reality is a lot more complex because obviously nothing is an isolated system. Okay. All right, so if a person did what that person in the top picture there is doing, what's eventually going to happen to their hands? Yeah, they're going to probably burn their hands. Depending on what type of metal that is, that could happen right away or much later. Okay? Not all metals conduct heat, okay, as quickly as others. Okay? But most of them do have a pretty low heat capacity and would heat up pretty quickly. All right? But the heat flows to that person's hands because of the second law of thermodynamics. energy flows from hot to cold. Okay? The hot part is obviously the part that's in the fire. Okay? But eventually that energy will move to the person's hands. Okay? And we talked about how that works, okay, the other day, because we talked about how particles will collide with each other. In the part of that metal rod that's hot, the particles are moving really, really, really fast. Okay? And when you move really fast, you run into each other. Okay? Well, eventually that collision transfers up the rod, okay, to the higher parts. Okay? It's kind of like, how many people have ever seen or been in a mosh pit? Okay? It's kind of like a mosh pit. If you're in the middle, you're bouncing around all over the place because everybody's jumping around and people are body surfing over the top. Okay, and yeah, that you're just constantly running into people. But eventually, on the outside, you might still encounter movement from the center that has kind of been passed through, almost like a wave, okay, through to the outside, even if you're not in the really dense part. Okay, it will eventually work its way out. Sorry, were you asking what a mosh pit was?
Yeah.
Okay, like at a concert, it's like the mass of humanity all standing there, jumping up and down.
Oh.
Yeah, especially at like a heavy metal concert, you occasionally get the really crazy guy who's just like throwing himself into other people. Okay, that would be the really hot particle. Okay, that's got a lot of energy, and yeah, it's kind of, you don't want to be around him. Okay, he's also the guy that will drop the body surfer because he's not paying attention. Yeah. Okay, don't body surf. You'll get dropped eventually. Okay. Okay. Or you'll get stuck up there. Okay. We once had a friend who was body surfing, and she was really small, and she basically spent the whole concert, okay, like just up there, and she couldn't get down because no one would let her down because she was really easy to hold up. Okay. Versus like the big dude who came with, you like crushed people under him. When you see the big guy jumping off the stage, get out the way. That's his own problem. Yeah, you'll get hurt if you try and catch him. See, valuable stuff that you didn't think you were going to learn. All right. So open system, closed system. Okay. So let's talk laws of thermodynamics here. Okay. First law of thermodynamics. I've crossed out the word and just wrote the word is because that's really true. The first law of thermodynamics does say that energy can't be created and it can't be destroyed. Okay. It does, however, leave open the possibility of both gaining energy and losing energy. Okay? That doesn't mean the energy is being destroyed, it doesn't mean it's being created. It is coming from somewhere else or going somewhere else in the forms of either heat or work. Okay? Because heat is a transfer of thermal energy and work is a transfer of mechanical energy. Okay, now, as we said, heat can be transferred, okay, or thermal energy is transferred through heat by the collision of particles, which at that level is really more like mechanical work. The particles are moving and they have energy and they hit other particles, okay? We just see it more as something, as warmth traveling through something else or from one thing to another, okay? But at the particle level, it's really more like a mechanical exchange of energy because it's actually a collision. All right, so it's important to distinguish heat from work. Okay, work involves the movement of matter from one location to another, whereas heat is a transfer of thermal energy from one location to another. Both heat and work can affect systems. All right, so heat and work are similar in that they're both transfers of energy. What's different is the type of energy being transferred. With heat, it's thermal. With work, it's mechanical. Okay, so if we look at my cart here, okay, we'll consider my cart to be a system, all right? I can change the energy of that system in two ways. I can put an electric heater right here and point it at the cart, and eventually the cart will get hot, okay? That would be heat. I'd be transferring thermal energy to the cart. Okay, and the system's energy would go up. All right, or I could just simply grab onto it. Okay, I'm not moving the cart, but I'm warmer than the cart. Okay, and already I can feel that the handle here doesn't feel cold. It felt cold when I first touched it, okay, but it's already receiving thermal energy from my hands. Heat is going into that system. Right? I'm not creating energy, I'm not destroying it, it's just going from one place to another, hot to cold. Okay? The other way is I can do work on it. Okay? I give it a push. I exert a force on it and it starts to move. It wasn't moving before. Okay? It gained some mechanical energy from me giving it a push. But very rapidly, what did it do? It stopped. Okay? I gave it a push, gave it some energy, and then where did that energy go? Because it stopped. That means it has to have lost all the energy I put into it. Where did it go? To the surroundings. Could you hear it when it was moving? Makes noise, right? Well, noise is caused by friction. Friction turns mechanical energy into sound, heat, sometimes light. Okay? All that energy, all that work I put into it, eventually just bled off into the surroundings as thermal energy, sound energy. Okay? It's all still accounted for, it's just not in its original form. But again, the law of conservation of energy has been obeyed. We didn't create any, we didn't destroy any, but we changed what it was and where it was. Okay? Everybody all right with that? That's what makes that boundaries of a system part kind of tricky. Okay? The surroundings can be a lot of things. Okay. Okay, so in that first picture, okay, she puts that hot metal rod into a bucket of water. Okay, what's going to happen to the energy of the water? It'll go up. Yeah, she's putting something hotter into the water. Energy flows from hot to cold. Second law of thermodynamics. So there it goes. Okay, to make that pogo stick work, okay, the person has to jump onto it. When they jump onto it, do they do work on the springs or the elastic part of the pogo stick? Okay, so they're transferring mechanical energy to the pogo stick. Now, if that pogo stick was an isolated system, once the person jumped on it, what would happen?
Would it just break?
Nope, it wouldn't break. If it wasn't strong enough, it would break. But let's say it's strong enough. Okay? If it's an isolated system, that system, once we do that work on it, can never gain or lose any energy. So what would the pogo stick do? It would bounce forever. Because it could never lose any of the energy the person put in it by jumping on it. Okay? Once that energy was put in, if it's isolated, an isolated system cannot exchange matter or energy with its surroundings. Okay? So once he gets that system moving, it can never stop. Okay? Is that strange? Yeah. Okay? That's because there is no such thing as an isolated system. We've never seen a situation where that can happen. Okay? Can we make something that's very efficient and would maybe move for a really long time? Sure we can. Okay? But it's never going to move forever. Okay? All right. So that's just showing the two different kinds. That's heat versus work. All right, so first law of thermodynamics, okay, like we said, is really just a restatement of the law of conservation of energy. It states that the total energy, including heat, in a system and its surroundings remains constant. Okay, here's where that textbook made a mistake. Okay, heat is not a form of energy. That should say thermal energy. Okay, heat is a transfer of energy. Okay, as soon as we say including heat, we're talking about it losing the energy. It's going somewhere else. Okay, so according to this law then, anytime we add any type of energy to that system, it should increase the energy of that system, okay, as either mechanical energy or thermal energy, okay, whichever, okay, it might in fact increase both. Okay, now the last paragraph talks about what we just did with the cart, okay, real world situations. Okay, in most real world situations, machines have moving parts that are in contact with each other. Okay, so in the wheels of that cart, there are little bearings. Okay, and in those bearings, there are metal pieces of metal that are in contact with each other. So as the cart rolls, those pieces rub against each other. Okay, what force is there? It's mechanical energy. What force is taking it away? The force of starts with that. Friction, right? That's why it made sound, okay? Probably the wheels and bearings probably got a little warmer because of that friction, okay? Like even something as simple as just rubbing your hands together, right? Right away they start to get warm because you're turning your mechanical energy of moving your hands into thermal energy because of the friction between your hands, okay? That sort of makes sense? Okay? Friction is affected by lots of things. It's affected by the materials that are rubbing together. Okay? It's affected by how hard those materials are pressed together. Okay? And that's one you can kind of observe really quickly. Okay? Just put your hands together, but don't push them together very hard, and then do this. Okay? They don't get very warm. Right? Push them together really hard and then rub them together. Okay? They get warm a lot faster. Okay? Friction increases the harder you push two things together. Okay? You'll learn more about that in Physics 20. Okay? It's completely true. You can kind of demonstrate it this way actually with mechanical instead of heat. Okay, there's two ways to move this desk. I could pick up the front of it and pull. Okay, pretty easy, right? The other way is to push the desk. Why is it so much harder? It's the same desk. One way was super easy. The other way I'm pushing as hard as I can and I can't get it to move. Friction. Friction is present in both, and it's the same surfaces. It's still the little tennis ball covers and the floor. What's different is how hard the desk and the floor are pushed together. When I'm trying to push this, I'm pushing down a little bit, right? I'm pushing the desk and the floor together even harder. That makes friction greater. Okay? When I pick up the desk, there's a lot less of the desk's weight pushing on the floor. So now it's way easier because those two surfaces are not pushing on each other nearly as hard. Okay? So there's less friction. Okay? So lots of things can affect how much friction there is, and thus how much energy would be lost. Okay. All right. Okay. How many people have heard of one of these things before? A perpetual motion machine. Okay. A perpetual motion machine is basically an isolated system. It's a machine that once put in motion should run forever. But you can't build one. It's impossible. Why? Sorry, Stella, I thought you were demonstrating exactly why. That was actually a good idea. Okay? Stella just pulled that desk closer to hers, and it made noise. If you have anything moving, you got parts rubbing together, right? What do you lose? You lose energy because of friction. That's why you can never build a perpetual motion machine. You would have to completely isolate it from all the forces that could cause it to lose energy. And as far as we know, that is impossible. Okay? There's always going to be energy losses. You can't build an isolated system. You can build a really, really closed system, okay, that loses very little energy, but you can never completely isolate something. Right? So you can never build a perpetual motion machine because it violates both laws of thermodynamics. Okay? For a machine like that to run, you would have to create energy because it would have to have energy added to it all the time to keep running. Okay? And energy always flows away from a high energy object, which means that system would always have to lose energy, which means it would have to eventually stop. All right? It's not possible to build a perpetual motion machine. Here's the other part of this. Even if you could build a perpetual motion machine, one that would just run constantly, what could it never do? Exactly. It could never produce energy. In other words, it could never do work. Because as soon as it does work, work is a transfer of energy. If it does work, it loses energy and it stops. Otherwise, if it doesn't stop, it's violating the first law of thermodynamics. It's creating energy. Okay? So even if you could make a perpetual motion machine, it would be nothing more than a scientific curiosity. It could never do any useful work. Because as soon as you connect it to something, it would transfer energy away and stop. Okay? So it would be utterly useless, other than to go, hey, I built one. Right? But it wouldn't do anything useful. Right? So people had this idea that they could build one, okay? But they do kind of violate the second law of thermodynamics. Okay? They also violate the first law. So here were some ideas people had for a perpetual motion machine. They had this wheel with like the ball bearings inside, okay? And the edges of the pie are kind of curved. So if it spun, the ball bearings were supposed to move to the outside, gravity would pull them down, and that would spin the wheel. But as they came to this side where they were moving up, they would go into the middle. Okay? Kind of like a conservation of momentum idea. I don't know if you guys have ever watched like a figure skater do a spin. Okay? When they tuck in like this, they can spin really, really, really fast, but they put their arms out and they slow down. Okay? This is the same idea. Put the ball way out on the edge and let gravity pull it down, and then when it has to go against gravity, pull it into the center where gravity wouldn't pull on, where its effect wouldn't pull on it as much. Okay, gravity still obviously pulls on it, but because it's in the center, it doesn't have as big of an effect, right? Now, is there still friction here? Yeah, there's friction here at the pivot point. There's friction along all of these things as the ball rolls. If I put that thing in motion, would it make sound? Sound's a form of energy. If I can hear it, it's being lost by that. Okay? It's not a perpetual motion machine. It'll stop. It might run for a while, but it'll stop. Okay? This one was the one I thought had some promise. Okay? Because a magnet's basically free, right? You don't have to put any energy into a magnet. It just attracts metal. But eventually all magnets will lose their magnetism. Okay? So for a while though, okay, this ball, let's say they're like a steel ball bearing, okay, it would go up towards the magnet, but as it gets close to the magnet, it falls through the hole. Okay? And then it goes down this ramp. But once it gets to here, it's got to open this door. Does that work? It's going to lose energy every time it has to open that door. And this machine doesn't work without that door, because all the balls would just stop here. Okay? So there's a flaw in that one as well. Plus, we would still hear, okay, the balls moving through there. There's sound obviously being produced. Okay? It's a good idea, but there's still a flaw in it. Okay, so second law of thermodynamics, okay, like we said, describes the direction of energy flow in natural processes. The natural processes part is important. We can actually go against the second law of thermodynamics, provided we put energy in to do it. Okay? It's actually what your refrigerator does. Okay? Your refrigerator is constantly overcoming the second law of thermodynamics. Okay? And you can see there the last part of that sentence says, never naturally from a cold object to a hot object. So that means I can artificially make it do that. Okay? Which is what your fridge does. Your fridge and your freezer both pump heat from a cold area to a hotter area, right? Thermal energy is always wanting to go into your fridge because inside your fridge is cold. Okay? That's the way that thermal energy would naturally want to go. Your refrigerator keeps it cold inside by actually forcing energy the other way. Okay? It absorbs thermal energy from whatever's inside of it, okay, and then pumps it outside to the surroundings. Okay? We actually call it a heat pump because it's like active transport for energy. It makes things go the other way. Okay? All right, so this idea that energy, especially thermal energy, always flows from hot to cold as heat, okay, was immediately recognized as a possible way to do work. Okay? If we know energy is going to flow from hot to cold and we put something in the middle, we can catch that flow. Okay? Same idea as a hydroelectric dam. Okay? I know the water's got to go from the mountains to the ocean. So if I stick something in the middle, okay, and make the energy of that water do some useful work, I can get work and energy out of it. Okay? So that was the idea behind the heat engine. Okay? If I've got a high temperature area over here and a low temperature area over here, thermal energy or heat is naturally going to flow from hot to cold. Okay? I just have to put something in the middle that can catch it. Right? And then I can allow that natural flow to do some useful work. Okay? So it would steal some, that would be the work done here, okay, going that way. All right? Everybody okay with that idea? So in a heat engine, okay, when heat in a heat engine flows from high temperature to low temperature, the heat can be converted into mechanical energy. All right, now, the first idea of how to make this work was, okay, this. This boat was supposed to be the first, sorry, that diagram's not going to make any sense yet, okay? I know it's just cheese and it makes no sense, but trust me, it'll make sense in a minute. Okay, so this was the first idea for how to use a heat engine.
Are you going to go back?
Oh, I can, but I want to talk about the heat engine. Okay, so this was the first idea for a heat engine. Okay, if I had basically two tanks in this boat, okay, and one tank was attached to a short pipe that was in contact with warm surface water, okay, and another one had a tank that was connected to a pipe that went down into very deep cold water. The energy would want to flow from the warm water through this turbine to the cold water. Okay, because when heat flows, it has to take kind of matter with it. So water would actually flow through this thing, okay, and then power the turbine, which would propel the ship forward. Right? What are some major flaws with this design? How long does that pipe need to be? If you have a ship, do you want to be dragging a super long pipe along that goes straight down? I feel like you're going to drag bottom and break that off a lot. Okay? And it wouldn't work as you get closer to shore, because then all the water would be warm. Okay? This would only really work in the deep ocean, even if it did work. Here's the other problem with it. Are this warm water and that cold water in contact with each other already? So what's the motivation of that water to go through the turbine when it can just circulate like this? That's the cheese diagram. Okay? If I have a mouse right here, okay, and it has an easy path to the cheese, why would it go this way? Well, that's what we're asking the energy to do. If it's already in contact with the cold water, why doesn't it just go on that straight line? Why would it go through here and then down? It makes no sense. Okay? It's a good theoretical concept that can get people thinking, okay? But that design is never going to work. Okay? The other part of it is that warm water and that cold water, at the most, might have a 20-degree difference in temperature. That's not a lot. Okay? It's not enough to have a significant flow of energy back and forth. Okay, sorry. In case anyone needed that. Yeah. Everybody all right with that idea? Okay, the idea of the heat engine? Okay, we actually use this technology to propel certain vessels. This is a jet engine. A jet engine is a heat engine. It works exactly like this, except it burns kerosene, okay, JP5, jet fuel, okay? It burns really, really hot, okay? So the part of the jet engine where the fuel is actually being burned is ridiculously hot. The surrounding air is, by comparison, very cold. So the heat flows very, very quickly. The bigger the temperature difference, the faster the energy flows through. Okay, so it very quickly flows past the turbine. Okay, that's the spinny part of the jet engine. Turns that jet engine, and because that turbine gets spinning, air is sucked in the front and blown out the back at an incredibly high rate of speed, which propels the jet forward. Okay. Yeah. All right, but it's the same idea. It is just using the second law of thermodynamics to propel something. Okay, you've got a hot area, you've got a cold area, and you stuck something in between them that could turn as a result of stuff going through it to generate power. Okay, everybody all right with that? Okay, turbines do a lot of energy conversion. That's how a hydroelectric dam works. Okay, as the water is going through, it's just turning a turbine, okay, with its mechanical energy to generate electricity. When we make electricity using coal, okay, we boil water, okay, turn it into steam. The steam is under pressure and it goes through a turbine, spins the turbine, generates electricity. Nuclear power, same thing. We boil water using nuclear power, the steam goes through a pipe, spins a turbine, generates electricity. Okay, so turbines are almost always involved in using or converting thermal energy into something else. Okay, now, my wife and I went to this cabin and they had a wood-fired hot tub. Okay? And as soon as I saw this thing, I'm like, oh, I gotta get a picture of that, because this is exactly what I teach my kids about in Science 10 physics. Okay, so here's how this thing's designed. This part here is the heating unit. Okay, so in the outer part of this metal container is water. Okay, it's connected to the tub. The tub, when we got there, was ice cold. Okay, because it was, I mean, it's obvious there's snow on the ground. Okay, it's not heated by anything other than this fire. All right, so it was really, really cold, but you can see there's two pipes going into and out of the hot tub here at the back. All right, so once you light this fire, the water inside this heats up. Okay, and when it heats up, it starts to move towards colder water, which is the tub. Okay, so the water moves through here, goes into the tub. Colder water is then forced through this pipe into the heater. And all you do is you get this current being formed because of the second law of thermodynamics. Everything is colder than the fire. All right, so energy naturally wants to go. Okay, by the time we got this thing really going, you could feel, when you put your hand in front of this part, you could feel the hot water circulating. It was almost like a jacuzzi. It was almost like a jet. Okay, right there, it was moving so fast as it started to heat things up. Okay, it took a really long time because we only had wet wood. Okay, so the fire didn't get real hot right away, but eventually, okay, we had a hot tub. It was great. Right? But all it does, okay, there's no electricity, there's no pump, nothing. It just relies on the second law of thermodynamics to move the water and eventually heat the water in the tub. Okay? That's all the water that's there. There's no water coming in from anywhere else. All it does is circulate the water in the tub through the heater. Okay? It's a perfect example of it. Yeah. When Grace comes back. All right, so we were talking about the heat engines here. Okay, jet engine is a heat engine, so it simply does exactly what we described before. Okay, it makes a hot area. The surroundings are cold. Energy wants to flow from hot to cold, and on its way through, it spins that turbine, which generates thrust. It can also generate electricity for the plane. Now, on the right is a pretty old school air conditioner. Okay, an air conditioner is a heat pump, just like your refrigerator is. All right, so we'll talk about how a heat pump works here. Okay, so the heat engine, we already talked about that. You can even do that with an electric motor and a cup of hot water and a cup of cold water. Okay, you can connect it and it'll actually spin a fan. Okay. All right, but a heat pump works like this. Okay, so a heat pump is the opposite. So when your refrigerator is running, you can feel warm air, usually coming out from underneath it. It's ventilated underneath, right? You can feel the hot air coming out. That hot air is the thermal energy that was captured by the refrigerator from material inside. Okay? And it's forcing it from the cold internal part of the fridge to the warmer surroundings. That's backwards. Okay? Heat should be going into the refrigerator because it's colder in there. And it does. That's why the refrigerator constantly has to run. Okay? But here's what the refrigerator does. It literally pumps the thermal energy out against the second law, just like active transport does in a cell. It pumps material the opposite direction that it's supposed to go. The caveat, the catch, is that you have to use, active transport has to use, well, yeah, your fridge has to use electricity, active transport has to use energy. Electricity is a form of energy. You can violate the second law of thermodynamics if you pay for it. Okay? You've got to spend energy to make it go the other way, right? Water doesn't naturally flow uphill. Heat doesn't naturally go from cold to hot. But if we use energy, we can make it go the wrong way. And just like we can pump water up a hill. So here's what goes on. The thing you can hear running in your refrigerator when it's running is the compressor. What the compressor does is there's coolant or refrigerant that circulates through your fridge. If you've ever pulled out the fridge to clean behind it, you can see there's like kind of a grating of metal, small like copper pipes, okay, that runs on the back of it. Okay? That's where the coolant circulates. Okay? Inside the walls of the refrigerator and the roof of the refrigerator also are little tubes, little pipes that contain the refrigerant. Now, the refrigerant changes state from liquid to gas as it absorbs energy. So you put food in the refrigerator, it's hotter than the air inside. Okay? That heat is then absorbed by the refrigerant, which is quite cold by comparison. The heat gets absorbed by that, and the refrigerant turns from liquid to gas, okay, as it absorbs the energy. Then it circulates down to the compressor. And the compressor, as the name would imply, applies pressure to it. When you apply pressure to a gas, you can force it back into a liquid state. But when you do that, it gives off all the energy that it absorbed to become a gas. Okay? It can't have that kind of energy as a liquid. So all you do is apply pressure to it, force it back into a liquid state, and heat comes out. That's the heat you feel coming out from underneath the refrigerator. Okay? The heat that is given off by the refrigerant, because it's being converted back into a liquid, okay, is being pumped out into the surroundings. Okay? Does that sort of make sense? Your air conditioner works the same way, but on a much larger scale. All right? You cannot use your refrigerator as an air conditioner. Don't leave the door open. Okay? It is only designed to cool the volume of air inside the refrigerator, not the volume of air inside your house. That is a lot more. Okay? The other part of it is, if you leave the door open, all the work it's done to cool off the inside goes right back into the open door of the refrigerator. Okay? It'll just run constantly till it burns out. Right? Your air conditioner is placed outside. Okay? Inside of your furnace, there will be coils, just like these. Okay? The air from your house is pumped through the furnace, which isn't running. Okay? It's not heating any air. But that air comes through, goes by these cooling coils, turns the refrigerant from a liquid to a gas, and then that liquid or that gas is pumped to the air conditioning unit outside of your house. Inside the air conditioning unit is a giant compressor. Okay? If you have an air conditioner, look in the top. You'll see it. It's a big tall thing in the middle. Okay? That's the compressor. Okay? In there, that refrigerant is turned back into a liquid, and the heat gets pumped out. Okay? When it gets warmer, and your air conditioner is running again, okay? When it's running, right over top. Not inside, over top. Okay? And you'll be able to feel the hot air coming out of it. That's the heat that was previously in your house. Okay? It's being pumped against what it should do to the hotter air outside. Making sense? So a heat pump goes against the second law of thermodynamics by using energy to move it the wrong way. All right, so I would say probably that stuff that is underlined there, okay, that would be the important stuff. Can I move it up yet? Is everybody done with this first bit? Yeah? No?